in our previous class we have seen the cut sets as a concept, and those concepts are very important, particularly in a set of problems which may be known as maximal flow problems. So, we will take up maximal flow problems and we will continue for next few classes, particularly also looking at probably the maximal flow minimum cost problems. But before really getting into those type of problems, there are certain important concepts which we should understand first with regard to the fundamental matrices. Now, there are certain fundamental matrices. The two of them are so important, they may be called fundamental circuit matrix and the fundamental cut set matrix. Now, if you recall, while we are identifying the cut sets and earlier also the circuits in a particular graph, we have understood that the spanning tree is very important concept, and because a particular kind of problems like a kind of linear programming problems or similar such problems, the solution is basically to be found from one of the spanning trees, right, which optimizes a particular problem solution. So, therefore, from the spanning tree point of view, if we really have to find out all the cut sets or all the circuits from a particular graph, simply by exploring we can see that sometimes it may not be possible to really identify all the cut sets. Much more important is how to find those maybe the fundamental ones from where we can actually generate all the remaining cut sets or circuits as required, right. So, let us look into this particular thing first and then we move over to the maximal flow problems. Now, consider a graph with respect to the spanning tree, that is E2, E3, E4 and E7, and find out the fundamental circuit matrix, fundamental cut set matrix, and show that the matrices are orthogonal to each other. So, this is the question that we shall take up now. Look here, please always remember these fundamental circuit matrix or fundamental cut set matrix, they are always defined with respect to a particular spanning tree. So, if you have another spanning tree of the graph, then the fundamental circuit matrices will be different, fundamental cut set matrices will be different. Is it all right? So, these fundamental matrices are always defined with respect to a given spanning tree. So, if anyone asks you find the fundamental circuits, immediately your question should be what is the spanning tree we are talking about. So, with respect to that particular spanning tree only we will be able to find out the fundamental circuit matrix or the fundamental cut set matrix. So, let us look at let us draw this graph here, that is there is a triangle here and there is a square here and then there is a connection. So, this one is E5, this one is E4, E7, then E6, then E1, E2 and E3, right. So, this is our graph and a particular spanning tree is given to us, that is E2. Obviously, there is nothing about this particular one can always choose another graph, another spanning tree of the graph and continue the discussions, but nevertheless let us go ahead with this particular one, right. So, this is the spanning tree. So, this is the graph G, this graph G, and the spanning tree S, spanning tree S equal to E2, E3, E4 and E7. E2, E3, E4 and E7. So, this is the spanning tree that we have taken and for a graph G, and then what we need to do first, we have to find out the fundamental circuits. We can have a matrix also, that is the circuits on one side and the edges on one side, and we can put 0 if the edge is not taken, 1 if the edge is taken. So, we can make the fundamental circuit, we can show in the form of a matrix, and that matrix is called the fundamental circuit matrix. So, you see what we have to do here, every chord gives rise to one fundamental circuit with respect to the spanning tree edges. This point you must remember, right? What you have to remember, that you see here these are the spanning tree edges. So, what are the chords? What is the chords? The chords are E1, E5, E6. There are 3 chords. So, how many fundamental circuits will be there if there are 3 chords? Because every chord will give rise to one fundamental circuit matrix, and if there are 3 chords, then there should be 3 fundamental circuits, right? This point you must remember. So, if you remember that, then you see every chord will give rise to, because once you have taken one chord, you cannot take another chord. So, if you take E1, look here, E1, E2, E3, that will make a fundamental circuit. All right. So, we can write here C1, we can write here C2, we can write here C3. Although we will not write C1, C2, C3, the fundamental circuits are actually shown not in terms of C1, C2, C3, but on B1, B2, B3. Why? Why not C? Because C is reserved for the cut set matrix. So, we write B1, B2, B3. So, B1, B2, B3 are my 3 fundamental circuits coming out of the 3 chords, and here we will not just write E1, E2, E3, E4, E5, E6, E7, right. We will use an ingenious way of writing this. What we shall do? We shall write E1, E5 and E6 first. Why E1, E5, E6? Because they are the chords, and then we write E2, E3, E4, E7. Now, look here, these you can think of a partition here as well. Now, E1, E5, E6, every chord will give rise to one fundamental circuit. So, we make a simple thing, we just make an unity matrix here. So, if you make an unity matrix, then you get those 3, because E1 is the first one, E5 for the second one, and E6 for the third one. If I take E1, what will be some spanning tree edges that will make a fundamental circuit? E5, E2 and E3. So, we put 1 there and zeros here. What about B2? When we take E5, then E3 and E4. E3 and E4. What about the third one? If I take this one, look here, E3, E4, E7, right. So, E3, E4, E7. So, look here, we have got our fundamental circuit matrix. So, just now for your information, just look at this particular thing. What we have, this is drawn in a different way, that is this side it is shown E1, E5, E6. So, 1, 1, 1, 0, 0, that is the unity matrix from the chord, and this is where the spanning tree edge is. All right. Now what we can do, we can also rearrange this one. So you see, this is our fundamental circuit matrix here, and what we have done, we have put the fundamental circuit matrix rearranged. So this is our matrix, the matrix is rearranged. How it is rearranged? Just look only this part, that this is the fundamental circuit matrix BF, and after rearranging we put E1 100, E2 which was 100 100, E3 111, E3 111, and we can put. So that becomes our fundamental circuit matrix, right. So this is our fundamental circuit matrix. So you understood that how to make a fundamental circuit matrix. Now the question is that if this is our fundamental circuit matrix, how do I get other circuits? How do I get other circuits? So just imagine B1 is given by E1, E2, E3, and what is given by your B2? B2 is given by E5, E3, E4, E3, E4, E5. So you see, simply do a ring sum. What is the ring sum of B1 and B2? Remember ring sum? In a ring sum, what happens? It's an union minus the intersection. So what is the union? All of them. What is intersection? E3. So E3 should be removed. So the ring sum will give rise to E1, E2, E4, E5. Can you identify E1, E2, E1, E2, E4, E5? Just see, can you see that circuit, right? So like this, you can keep on doing these ring sum operations to identify other cuts, other circuits. Is it all right? So now look here, that we have only 3 fundamental circuits, and we can work with them only. There is no need to really find all the circuits all the time. Is it all right? The fundamental circuit matrix is sufficient to generate all the other circuits by doing ring sum between them. So we can do ring sum between B1 and B2, B1 and B3, B2 and B3, B1 and B2 and B3. Is all right. So we can keep doing all these ring sum operations, and we can obtain all the circuits of this particular graph, right. So this is the advantage of the fundamental circuit matrix. Once we generate the fundamental circuit matrix, obviously remember with respect to the spanning tree only, another spanning tree, another fundamental set of fundamental circuits, right. So once the spanning tree is fixed, you can get the fundamental circuits, and you can generate all the circuits by ring sum operations. All right. Now after that, let us look at the fundamental cut set matrix. Again, what we do here, fundamental cut set matrix. So C1, C2, C3, how many will be there? How many spanning tree edges are there, right? Like in fundamental circuits, we have every chord gives rise to one fundamental cut set. Here every spanning tree edge will give rise to one fundamental cut set with the chords. All right. So every spanning tree edges will give rise to one fundamental cut set with the chords. So how many cut sets can you think of, fundamental cut sets? How many spanning tree edges are there? 4. So, you can think of 4 fundamental cut sets. So, these are the 4, and let us write these E2, E3. This order is not very important because finally we will again make it sorted and E1, E2, E3. So, you can write this side first, and these are the 3 chords E1, E5, E6. So, again take the unity matrix with regard to, see earlier we took unity matrix with regard to the chords, now we are taking unity matrix with regard to the spanning tree edges, right. So, right, now look here, if you take E2, then this is our cut set, that means you will take E1. So, this is fundamental cut set 1. Now, if you take E3, only E3, right, then you can take only chords, mind you. So, which chords will you take? Only this, because you cannot take another spanning tree edge. So, all the 3 chords you can take, and that will be your C2. So, you have taken E1, E5, E6, all of them, and C3 is about E4. So, this is E4, so this is C3. So, C3 would be E4 and then E5 and E6, alright. And what about C4? It is with E7, so just this one, so this is C4, right. So, the C4 would contain E6 and E7, E7 is already there, so we have E6. So, you see we have now generated the fundamental cut set matrix. So, we have the fundamental circuit matrix and we have the fundamental cut set matrix. So, here you can look that we have made in the slide already this answer, and that is the fundamental cut set matrix, right. Now, an interesting question, if you look at the fundamental cut set matrix and the fundamental circuit matrix BF and CF, they are orthogonal to each other. You see, will not go very deep into this, but at least this much will tell. If we multiply BF with the transpose of CF, then we get a null matrix. Obviously, not really null because these are all binary matrices. So, 2 should be taken as 0 only. So, this you can call as phi mod 2 matrices. That means the entries will be either zeros or 2s. Is it all right? So, the advantage is that if we have one matrix, it should be possible to generate the other matrix by some operation. And lot of applications are there. If I have a switching circuit, if I have the circuit matrix, it should be possible to generate the connections, not from cut set matrix, but another relation where we have the incidence matrix we can generate. But anyhow, we will not go into those things, we will simply look at that how they are orthogonal. So, let us look at that here. This is the fundamental circuit matrix and we have put it in this manner E1, E2, E3, E4. Similarly, this is the fundamental cut set matrix, and that is also we have arranged in a transposed manner, because if you have to do matrix multiplication, this side and this side should be exactly same. So, if this is 3 by 7, this should be 7 by something. So, this is 3 by 7, this is 7 by 4, and the result will be 3 by 4. So, this is the result that you get. Just look here, if you multiply BF with CF transpose, then we get a null matrix, obviously in the mod 2 domain, right. That is, entries are either zeros or 2s, right. So, that is how we say that these two matrices are orthogonal to each other. The advantage of orthogonality is that within certain limitations and assumptions, if we have one matrix, it should be possible to find the other one, all right. Anyhow, this is the essential idea of the fundamental circuits. Now, let us see how we can use them in maximal flow problems. So, first and foremost thing, when we take up the maximal flow problem, the first thing that we need the idea of what is known as a flow network. What is a flow network? A flow network is a simple connected, weighted and directed graph. Alright. So, what are the things? First of all, it is a simple graph. That means there are no parallel edges and there are no what is called self loops. That is why it is a simple graph. I think you know that simple graph is a graph which does not have any parallel edges or self loops. So, it is a simple graph. Second, it should be connected, right. That means connected means it should not be having components, and it should, that means from every node to every other node there should be what is known as a path available. Like here S to T, look here there are paths, S to 6 there are paths. So, between every pair of nodes there are paths. So, it is a connected graph. Thirdly, it is a weighted graph. What is meant by weighted graph? That means each edge is having a weight assigned to it. What could be that weight? The weight is that each edge or each arc is having a forward and reverse flow capacity. That is how it is become a directed graph, because if you go S to 2 then the capacity is 9, and if you come the reverse direction, that is 2 to S, capacity is 0. That means here there are some arcs like 3 to 5, look at 3 to 5. So, a flow of 2 is possible between 3 to 5, but a flow of 3 is possible from 5 to 3. Is it all right? So, that is what is the weight all about, and that is how the direction comes in. Is it all right? So, this is a flow network. What is happening in the flow network? A flow is coming at the S, that is called the source, and the flow goes out of the sink, that is T. So, a flow is coming at S and the flow is going out at T. So, what is the maximum possible flow that can come in S? That is the question, right. So, we have a flow network and the question is how much maximum flow is possible in this particular network. Is all right. And second question is that what should be the pattern of that flow, right? What should be the pattern of the flow? Now, why do we want to know all this? You see, there are very important questions that are there in all types of network. This network could be a transport network, road network, communication network, telecommunication network. Is all right. There could be different types of networks at different domains, and in all of these domain a common question is that how much flow is flowing through a particular path, because there are demands and those demands are to be satisfied, right. So, what could be what are the things that we have? We have the capacities, we can change the capacities. You see, if we change one capacity, the entire flow network may change. So, you see, just look here, if you change probably a 5 to T capacity, 5 to 0, you make it say 7 and 0, probably the entire flow pattern will change, and that would might affect this another link 4 to 6 also. So, it is not like that 5 to T let us increase the capacity, automatically it would mean that in its effect would be maybe in another link. So, person who is looking at the total network, no, you cannot really think of just one particular link and then increase capacity or decrease capacity, because the person knows that its effect could be on the other part of the network, and that is where the design comes in, right. So, it is not simply find the flow that is available, but also what is the impact of the change of capacities and how that is actually going to affect the entire network. So, such questions, the answers to such questions are extremely important, and for all types of network such kind of analysis is very much required. So, let us see how some of these things are useful and important. Now, there are some very basic assumptions. Some of the assumptions are given here. There are infinite node capacities, lossless flow for each arc, and no minimum limit for flow. So, three such assumptions we are given. In fact, there is a fourth assumption also. There is a single source and there is a single sink. So, let us take a particular example. Supposing we have a flow like this is source and this is sink. So, let us take a particular network. Let us say we have some very simple network. Let us take 1 and 2, then 3 and 4. That is all, nothing else. So, if we take this very simple network and let us say these are the flow directions, supposing, and 2 to 3 is possible, 2 to 4 is possible, 4 to T is possible, and 3 to T is possible. Alright, and 1 to 2 is also possible. Just take only this much network, and let us say we have 5 0, 5 0, 4 0, 3 0, 2 0, 6 0, 7 0 and 5 0. Just imagine and see a flow is F that is going out and F that is coming out. So, let us consider this flow network, right. So, what are those assumptions? Single source, single sink. Second assumption, infinite node capacities. Number 3, lossless flow. Fourth, no lower limit in any of the arcs. So, let us see these assumptions, what are their implications. So, first one, single source, single sink. Here if you really look at that, here if we have a single source and a single sink, what happens if there are multiple sources? Imagine a network where we have S1, 2, this kind of network, and this is a source, this is also source, and this is a sink. What to do then? What we can do? We can make a super source S dash by connecting all the sources and assume a single flow is coming with infinite capacities to these connections, right. So, this is an infinite capacity, this is the infinite capacity. So, you can transform a single multiple source, multiple sink problem to a single source, single sink problem by connecting all the sources to a super source and all the sinks to a super sink. Alright, that is possible. The second one, the infinite node capacities. Look here, the flow of 5 is coming to 1 and flow of 4 is going out of 1, or it can go here 3. Now, question is that if the node 1 cannot handle the entire flow of 5, what will happen then? What would happen? It would restrict the amount of flow that is possible. Is it all right? One hand you have this flow of 5, suppose the junction capacity is only 4, then only flow of 4 can come there, not the entire 5, right. So, initially we assume that all the nodes are having infinite capacity and they are not going to give any constraint to our flow problem. The third assumption says that flow is lossless. That means, if a flow of 5 is coming from here the entire 5 is reaching this node. We know sometimes that there could be a loss during the transit. The assumption here is no such loss is available. The fourth one is that no lower limit in any of the arcs. Sometimes what happens that, see, supposing the lower limit here is put as 0, the reverse flow is 0, right. Reverse flow capacity, not just not the lower limit, the reverse flow capacity is 0, but suppose sometimes what happens in the water pipeline networks, particularly in the cold areas, there is a minimum flow that has to be maintained, because if you do not do that, water may actually become ice, and when water becomes ice, its volume increases, pressure develops and the pipe may burst, right. So, a minimum flow must be assigned. So, these are our basic assumptions with which we shall consider the flow network problems, and all the knowledge that we have got about the graph theory, the cut sets, the spanning tree and etc., we shall see how all of these are useful and important, and those we will discuss in the next few classes, right. So, thank you very much.